Okie dokie. So today what we're doing is we are starting our new unit, and our new unit is going to be learning about functions, which we kind of know some stuff about already. So it's not totally new. It's using the information we've already learned. The other thing about today is that these notes, this first section can be found on, again, page 267 in your textbook. So that way you can just write in there so we don't have to write down like all this information. So today what we're going to be doing is we are going to be representing relations, and we'll get further into like what is a relation later this week, okay? But we are looking at a function. So if you remember, we've talked a little bit about functions being input and output, and functions follow a rule. So there's a rule for when you put something in, how it comes out, and that's part of what we're going to figure out today. So looking at number 1 here, it says, to achieve orbit, the space shuttle must travel at a rate of about 5 miles per second. So this is our first key piece of information, is them telling us about the rate. So again, the rate of about 5 miles per second. The table shows the total distance, d, that the craft covers in a certain period of time, t. Write an algebraic expression for the distance in miles for any number of seconds, t. So, first thing we need to do is we need to look at, let's say, the rate. So I'm going to make some notes off to the side here. My rate was, again, the 5 miles per second. And we know that rate can also be represented as slope. If we think back to our previous unit. And then if we look at our equation, y equals mx plus b, if you look back to this equation that we all know so well, we know that y should be representing my total, my m is representing my rate, my x is going to be representing my time here, right? This is going to be my input. And then my y-intercept here will depend on the situation. So when we think about this, if no time has passed, have I traveled any distance? No, right? You didn't go anywhere. So this would be passing through the origin of 0, 0, and that's why there's no b here. Okay, so write an algebraic expression for the distance in miles for any number of seconds t. So my distance is represented by d, so this would be d equals, and then my rate, which is 5 miles per, and then instead of seconds, we're putting t to represent seconds. So 5t. And then that's the equation that represents this relation. So if we double check it, if I substitute in 1, I get 5. If I substitute in 2, I get 10. If I substitute 3, I get 15. Substitute 4, I get 20. 5, I get 25. So describe the relationship in words. So the relationship in words would be that the shuttle travels 5 miles for every second. The shuttle travels 5 miles, every second. Yes, ma'am. Okay, so then we get down here and we're going to graph the ordered pairs, describe the shape of the graph. So the first thing is just a couple reminders that this is going to be my x-axis, and that is going to be my independent variable. And in this case, it's already told me that's going to be represented by t. You can see like a little tiny t there. So this is going to be time in seconds. And again, this is always going to be my input as well. Then when I come over here, it already tells me it's going to be D. So this is distance. I got to rotate this. I'm sorry. Distance in miles. And this is going to be my y-axis, my dependent variable, and this is going to be my output, or the total amount. Okay? Now, if you were really solving a problem, all this side stuff that I just wrote, you don't need. We don't need to write all of that. We're just using that for note-taking purposes. So when I solve problems later on, I remember this information about my graph. Okay? So then when we come up here, again, this here is going to be my X. And my X is my input. It is my independent variable. This over here is my Y. This is my total. This is my dependent variable. So then each one of these forms an ordered pair. So like the first one would be 1, 5, 2, 10, 3, 15, 4, 20, 5, 25. And if we remember, when we thought back to this problem to begin with, we discussed no time, no distance, right? Distance hasn't happened if time hasn't started. So we know we're going to start at the origin, which is here. And then I have 1, 5. So I go over 1, up to 5, 2, 10, over to 2, up to 10, 3, 15, 4, 25, 25. It always makes it so nice when they make the graph for you. Okay, so we have something that looks like this. We could also note to ourselves that it's linear because it's a straight line. Now, one of the things I noticed prior to going to break is that a lot of us forgot like what a graph represents. So in this situation, we're starting at the origin. You cannot have a line that's pointing off into this area down here because that means negative distance and negative time. There's no such thing, right? So we have to make sure we only have one arrow on our line. Okay, if you drew a line and there's 2 arrows, you would lose credit for that because that is not correct. So there's a 1 arrow line extending because to our knowledge, the spaceship currently just is going. Like we don't know if it teeters off or what happens. Okay, so remember the rules, use a straight edge, arrows at the end. And then we need to label our axes with the information about the problem. Okay, so that's what it should look like. Then if we take a look at our next problem here, this is about Paul. This problem is going to be located on page 271, I believe. 271. Okay. So it says Paul earns $25 for grooming a dog plus $18.50 per day for boarding the same dog. So when we read that, we know that this 25 is going to be like my flat one-time payment. So we have a flat payment of $25. Sorry about that. And then we know that the dog, $18.50 per day. So this is going to be a rate of $18.50 per day. When we go back to the flat payment of $25, it says Paul earns $25 for grooming. So grooming a dog means like you're giving the dog a shampoo and a haircut, okay? And obviously, like you're only going to shampoo and haircut the dog once, right? Like you don't shampoo and haircut the dog multiple times. So this is why it's a flat payment, because you're only grooming the dog one time. And then the $18.50 per day is the rate for how much we charge for the dog to stay overnight. So we're going to write an equation to find the amount of money Paul earned, M, for grooming a dog once and boarding it for any number of days, D. So it tells me here my M is going to be total money, and my D is days boarded. And then I just want to go back to this idea of the equation y equals mx plus b. So this is that slope-intercept form. You've been using this since course 2. You just don't realize it. Because in course 2, we wrote linear equations from word problems, which is exactly what we're doing right now. So here are my reminders. This here is total. We just wrote this up above. This here is rate. Input, this is initial fee or one-time fee, initial value, y-intercept. Okay? So based on this information that we have here, the equation that I'm going to need to write, this page is squishy, so I'm running out of room, is going to be M equals, this is $18.50 per day plus $25 grooming fee, which is that one-time fee. So this is following the same pattern as the last problem where we have total, rate, one-time fee. Okay, if we keep that pattern in mind, it makes it pretty easy to write these equations. So then down here it says make a table, find his earnings for 5, 6, 7, or 8 days, then graph. So my X is my input, which is really going to be my D here. And then my output is Y, but we're calling it M in this problem. And then in the middle part is that equation we just wrote, which is 18.5D plus 25. And we're solving for 5, 6, 7, and 8 days. So then what we're going to need to do is we're going to take the 18.5, substitute 5, and add the 25 to it. So this obviously is going to involve you doing some math, which again, I have a squishy paper here, so I'm going to need to get out another piece of paper in order to do some scratch work since we're not using a calculator. So 18.5 times 5 is 92.50 plus the $25. So 117.50. And now I have the 18.5 times 6 plus 25. So if you pay attention here, all I'm doing is adding another 18.50. So instead of doing all this crazy multiplication again, all I have to do is add another 18.50 to this. So that's a 6, I don't know, 136. So then you're going to finish out this chart here. Which means you should be doing math and not waiting for me to do this for you. And then my D is going to be days boarded. And my M is total money earned. And then again, I'm going to chart this. So one thing I want to point out is that they chose to make a break in the graph. A break is that squiggle there. And that is so we don't have to have an accurate scale going from 0 to 110, because that would make this a really, really large graph, right? So instead we do this break and then we can start the scale where we want to start it from. So we're starting on day 5, which is going to be the 117.50. I don't know, so something like this. And then due to this break, that is definitely making it kind of weird because we're not going to be able to pass through the origin currently. So we are going to start just at this bottom point that we have here. And it looks something like that. Because again, if I extend this, the origin, the 0, 0 is going to be like way down here off the page. So we can't represent that currently. Okay. And then that is what our graph should be looking like. So today, this is not really anything super new. We're writing equations from word problems and we're graphing them, which is everything that we've worked on before.